Students, welcome to lecture number 15 in this course. So, we will be starting a new topics today, that is the statistical and computational approach in machine learning. But before that, let us see what we have done till last class. So, for the last almost like a 10 to 12 lectures, we have discussed various aspects of the connections between processing properties and the structure. That is the material tetrahedron. You can see on your screen that processing is going to govern the structure, and in turn structure will govern the properties. And we are interested in the performance of material, right? That is what is our job is. So, performance is nothing but combinations of the properties which are used, and we always need to use characterization to see whether a particular structure has been obtained or not. We use different kind of characterization tools, and each of these characterization tools generates a lot of data. So, therefore, data is important in machine learning. Data can be obtained directly from these experiments, which is actually very good data, or you can be obtained from theoretical calculations using computers. So, either way, this particular tetrahedron provides you the global perspectives of how materials can be designed. If you want to have a new material to be designed with certain set properties or target properties, what you do is to first understand the structure, what is required for that properties, and then you go back and do some calculation to know what kind of processing routes can provide us that kind of structure. So, this is basically a reverse kind of step. First you have properties, then you go back to the structure, and then select the processing routes which can provide you the structure. And to get the structure, we have to characterize the material. That is why characterization comes at the center of the tetrahedron. And finally, the properties obtained. If the target properties are obtained, then we are happy. If they are not obtained, again we go back why the target properties are not obtained. This is kind of feedback loop. So, in the last so many lectures, we try to understand the basic nuances of this correlation between processing, structure and the properties. And at the end, we talked about processes. Obviously, I can't discuss everything in this class because of vast nature of these processes, as well as the time constraint I have. We talked about certification processes, we talked about powder metallurgical processes, which allows us to use particulates as a starting material, and then process is to form components. Then we discussed about deformation processes, like starting with any ductile material or solid materials, whether can we deform and get certain shape or not. But other than that, we also have material removal process, in which we can use a ductile or a brittle solid and machine the material by different kinds of machining techniques available in this world. But I did not discuss much about this because that is a different domain, and if start discussing about machining, it will take a lot of time. So, I think if you are going to use machining as one of your tool for material shaping operation, then you better read this particular topic and understand what are the different features or different aspects of machining which are required for you to do modeling. So, that is what it is. So, these pictures I have been showing you for the last 3-4 lectures, that shows you different kinds of processing techniques available. And finally, we are talked about solidification, deformation processing, and in deformation processing, important aspect is stress needed to plastically deform a material, that must be either compressive or tensile or shear, but normally we use majority of the process uses compressive, because compressive loading will allow material to deform without any failure, like rolling, forging, extrusions are the examples of compressive forces utilized for different kind of deformation processing. Similarly, tensile process used only for one process, stretching of the metal or stretching of the material. If you want to stretch something, stretch forming, that is the only technique, probably better methodology method, better word or better phrase is stretch forming, I would rather say. Stretch forming is what is using only tensile force. Then you can have bending forces which can generate tensile and compressive components, and each of these processes can generate shear stresses. That is very clear. But you also need to know about the material behavior per se. I gave you some fundamental equation. One of these is this. This is nothing but true stress is equal to K epsilon to the power n, right. That is very fundamental as you understand. And here the material parameters are K and n. K is the strength coefficient and n is your strain hardening exponents. So, you must have a data consisting of K and n if you want to characterize the flow behavior of any material, and that is the key aspects one has to know. Although the relationship is well known, but description of these kind of relationships depends on the values of K and n. And I showed you in previous lectures that n is always less than 1. That is why there is a nonlinearity come into picture. When you see the stress strain curves, they are nonlinear in terms of stress strain. So, initially you have a elastic portion, then it start become very nonlinear, right. And thus nonlinearity is basically because of the value of n. But there will be materials where n is equal to 1, but they are peculiar materials or they are very exceptional materials. Normally n is always less than or equal to 1. N can be 0 also in some materials which are perfectly elastic, but they are does not exist in the world. That is one of the things you have to understand. But for metal forming operation, we are not interested in elastic part, we are only interested in the plastic deformation regime or this regime. Okay. This is what is important for metal forming or deformation processing process, whatever people can call it. Both the words are true actually. So, in that sense, this is one fundamental equation for you to dwell on and understand the effect of this. Well, that is what is shown in a better way. So, you will be given values of K and n to characterize flow behavior of any materials. Other than that, you can also have values of yield strength, tensile strength, fracture stress, strain to fracture and uniform strain till necking. Remember what is necking and how it is described in my previous lectures. Okay. So, therefore, this curve, this behavior is important when you start any deformation processing of any material. Without knowing much of this, one cannot determine what kind of deformation processing will be used for a particular set of material to get a shape of the components. Well, other than that, you can also have other things like what is known as average stress, which is nothing but area under the curve, and that average stress I already told you is given by this, is nothing but K epsilon to the power n divided by 1 plus n, right. This is nothing but integration of the stress strain curve. Integration of the stress strain curve I have shown you, the whole area is integrated, then you get the area under the curve, that is, and divide by the. So, that is what is basically known as average strain. You can see that average flow stress, and this is important in many cases because that is what is used to calculate the power of the press or the hammer which will be used to deform the material, because this is average stress. Now, if you multiply it with the with a particular number, that will give you the requirement of the machine to get a particular level of deformation in a material, and this is why it is used. And that is what I shown you here, average flow stress. Whatever discussion I made is shown in this picture nicely, and this is and after that, other than that, another important variable is temperature, what we discussed in the last class also. And based on temperature, deformation can be divided into 3 categories: cold, warm or hot. If you want to decide on which one you will be using for a particular material, you must know what is what, right, what is cold, what is warm, what is hot working, and this distinction is done based on the recrystallization behavior during deformation or after deformation. As you know, if you deform material, you create a lot of defects, and these defects actually are primary agent for having plastic deformation. And therefore, initially if you deform any material, let us say you take any aluminum piece of aluminum and start hammering, what it will do? It will create a lot of defects or dislocations basically, especially for the sake of FCC aluminum, and these dislocations then will not find enough time to arrange themselves properly. They will be haphazardly arranged in the material, and that increases the energy of the energy due to deformation. It will increase quite a lot. Now you start giving heat, or you started increase the temperature of the material. First thing will happen is that this dislocation will try to arrange themselves properly, because they are early arranged in a haphazard manner. So energy was very high. So they will try to arrange in a very nice manner so that they can reduce the energy, and this is what is known as a recovery. And this happens primarily most of the materials. The recovery leads to increase of electrical conductivity. So simply by measuring electric conductivity, one can measure what is the recovery. And then if you further increase temperature, new grains, strain-free grains forms out of these deformed grains, and that is what is known as a recrystallization. Because new grain form, that is why it is called a recrystallization. Crystallization means formation of grains, and re means again. And this will be fine scale grains without any stress, without any defects present at the beginning. And still if you increase temperature, these grains will grow, and that is what is known as a grain growth. So normally it has been found the recrystallization of any material happens at melting temperature and absolute scale divided by 2, what is called Tm by 2. Okay, that is what is actually happens in most of the cases. So now we know that Tm is well known in the materials. Tm is defined in material. So simply by taking half of that in absolute temperature scale, one can find out what is the recrystallization temperature. So hot working is defined as a working which is done above this temperature, recrystallization temperature above 0.5 Tm, and cold working is always discussed, always consider working at a temperature less than 0.3 Tm, and between 0.3 Tm and 0.5 Tm any working is done called as a warm working. That is typically how we define these three designs of hot working, cold working and warm working. These three are defined based on that. So here I am given again same thing. So hot working is what above the crystallization temperature. This is very important for you to know why hot working is used. In practice usually is performed above 0.5 Tm, and metal will soften at the temperature and it will enhance the working above this level. And in last lecture I showed you how to calculate these hot working temperature or Tm by 2. So this hot working actually is useful because it decreases the yield strength of the material and it increases the ductility significantly. In fact, strain hardening copy exponent N will become very small at high temperature. Theoretically speaking, it can go to 0, but normally it does not go. And strain coefficient is substantially low here, K actually. So therefore, as compared to room temperature, therefore material can be deformed very easily. But the problem is at high temperature, if you want to deform at different strain rate, then the stress required increases, and I discussed a lot and I will discuss again. Now cold working is performed at less than 0.3 Tm, and this is important for mass productions operation. Cold working is very good because it does not lead to any surface change, and therefore no machining or minimum machining is required, and therefore cold working can lead to near net shape or near net shape forming process in the working. Warm working is done between 0.3 and 0.5 Tm, and this is there is a dividing line between cold and hot working, and that domain between 0.3 and 0.5 Tm, this is what is used. But there is very thin line between cold working and warm working. One can use warm working at 0.5 to 5 Tm also. So hence these are the three defined working regimes which are shown. Now there comes the effect of strain rate. Third factor is the strain rate. Okay, temperature, stress, and then third factor is strain rate, sorry. And strain rate is very important, okay, as you know. Why it is important? Because it affects the flow stress very significantly. And the fundamental equation is this: stress is equal to C epsilon to the power m, where C is a constant and m is the strain rate sensitivity. What does it tells you? It tells you that effect of strain on the stress is always always marked by this factor m, and it can be measured easily from this equation. But factor you should remember is that at room temperature strain rate has no effect, virtually no effect on the stress, but as higher temperature strain rate has a stronger effect on the flow stress. So, the hot working conditions you have to be very careful about deforming at high strain rate, because stress may increase very substantially as you increase the strain rate, right. Let us say the curve at 1200, you see at room temperature, at the curve is flat, but at 1200 curve has a definite positive slope. So, that is the major problem actually in terms of the flow stress where we are as a function of strain rate. Then I talked about a little bit of powder metallurgy. Other than that, the strain rate, you remember the friction and lubrication is also important factor in metal forming processes. You have to consider the frictional aspects very significantly, because we are using die and punches, and in these contacts the friction is significantly high. So, one is to use lubricant to reduce the friction, heat due to friction. So, these are the 4 fundamental factors: stress, temperature, strain rate, friction and lubrication. One has to remember during design of any processes, deformation processing. So, in terms of powder metallurgy, these are particulate processing of materials. We did not discuss much, only thing we discussed is that we need to have powder, powders are mixed together, then they are compacted in a die and followed by sintering at high temperature, and compaction leads to green compacts, green products actually, the products in which particles are bonded not very strongly. But after that, if you sinter it, sintering leads to mass transport or diffusion, and that makes the bonding very strong. And powder metal is very important because there are many components like tungsten, I showed you last lecture, cannot be processed by other than powder metal processing, and tungsten is widely used in various applications, starting with incandescent bulbs to missiles or even many of the high temperature applications, and that requires you to sinter, and sintering can be done in this way only what I discussed. And also PM processes has produced very low waste material, almost 97% of the powders are converted to product, and you can also use PM processes to make a material with specified level of porosity, that is in filters or well pigmented bearings or gears, that kind of porosities are widely used. This is an incandescent bulb, I showed you this is made of tungsten filament, you can see, and these tungstens are basically powder metallurgical process. There are many automobile products like bearings, gears or even connecting rods, they are produced also by powder metallurgy routes. Cutting tool inserts is the most important example I showed you, that many of the cutting tool inserts are basically tungsten carbide based materials. Tungsten carbide cobalt is what is used, one can use starlight also. So, they are all powder metallurgical produced material, and they are very important for the economy or for the cutting. And tungsten carbide is basically the one which is important. Other than tungsten carbide, copper, nickel, refractory metals, molybdenum, tungsten, they are also powder metallurgically processed. And what happened actually when you put the powders inside a die, basically they initially arrange properly, and that arrangement is depends on how the particle size, shape and their geometries are. So, after this mixing, particles are placed inside a die and then they are basically pressed by these punches. Once you press, you deform them slightly or press the powders little bit more, and that provides you a very nice compact, right. And this green compact then can be handled easily, and this green compact is then placed inside a furnace heated up to high temperature, and this sintering is done. That is what is happened after sintering, you get a nice sinter pellet. You can see that in the green compact you have very fine pores present, but in the sinter product very less number of pores are present. Sintering is a thermal treatment process, and this basically happens by mass transport. You have to understand, you can have both solid state and liquid state sintering. Solid state sintering is widely used for many of these materials in which no liquid is forming. Liquid phase sintering uses liquid, you can have transient liquid phase or you can have permanent liquid phase sintering. Most of the tungsten alloys are using permanent liquid phase sintering, you have a large amount of liquid is produced and done that. And this is what is sequence of the sintering shown. You have powder particles, and these particles are basically arranged this way, they form a neck, and the neck slowly goes and then sintering happens in these powder particles. Well, that is about the sintering processes. Now, as I told you, we are going to start discussing about the basic statistical tools or the machine learning tools. So, let me go back to your first lecture what I told you. AI is basically now a very common word used by everybody. If you talk about even a school children, they also understand what is AI. But AI simply does not mean it is artificial intelligence, you have to understand that. AI is what? AI is the ability of any machines or computers to mimic human decision making power. We have a lot of decision making capabilities, right, and problem solving capabilities. Can we mimic that? That is what is done by AI. Okay, you must have heard that recently Google launched AI machine called Gemini, and it will be soon attached to your Google Gmail or Google kind of workspaces, and this Gemini will allow you to do many things which a human can do actually. So many of these decision making processes for which we need our interventions can be done by Gemini, and there are many other ChatGPT like AI tools which can do this kind of aspects. But major component of AI is what? It's machine learning and deep learning. Okay, and machine learning is basically what? It is a process by which machine automatically learns from existing data. We'll talk about a little more on these aspects. What is existing data? How this can be used? But remember, machine learning requires a structured data. You cannot use any data, by the way, in machine learning. But deep learning can require any data, unstructured data, structured data, data in the form of text, images, or even any other format, doesn't matter. So our discussions in the next 20 lectures will be first focusing on machine learning, where we'll talk about how structured data can be handled. And then once you learn that aspect very clearly, we'll go into deep learning, where you can use the unstructured data like text, images. So ML is nothing but a particular process by which machine automatically learn from the existing data. But still it requires human intervention, otherwise it cannot learn all these things. And so I'll also let me discuss what is the difference between ML and the conventional approach. I've been talking about conventional approach quite a lot, right? And conventional approach means trial and error. Very simple. If you want to make a pot, so suppose you are a novice person, you are not an experienced person. So you take a piece of loaf of mud and start giving it shape, right? Initially you will be failing, right? You may not be able to get a proper shape. But upon a lot of experience, a lot of practice, you will get a proper shape of the pot. Okay, that is what is trial. So trial means you make several trials, several failures. Many times you fail and you learn from the failures, then you get your things, knowledge or experience, everything you gain, and then use that knowledge experiments to get a success. That is what is called trial and error experiments. This is very common in all spectrums of engineering. And material science, it's one of the base actually. So many people have discovered a lot of new materials simply by trialing with their own practices, and that's what is called trial and error things. But trial and error can give you sometimes success, sometimes it will not give you success, and the success rate also can vary depending on how you are doing it. If you are not learning fast from your failures, then you will be making more mistakes. So life is like that. You will be always making some mistakes, but you got to learn from the mistakes. Computers are very good at it, right? Now we have tools, or we have basically theoretical tools like quantum mechanics, molecular mechanics, many other kind of tools available. Tools are nothing but methodologies or equations, whatever you call it. Okay, in the textbook I've given you so many equations in the different parts of my lecture, right? The last so many lectures. So quantum mechanics is also we discussed, that has a particular methodology which based on a simple Schrodinger equation. Well, it's not a simple equation, but it looks like a simple equation. It's nothing but energy balance. Then you can also have molecular mechanics like what is known as a MD, okay, molecular dynamics. So this provides us the theoretical background by which you can do calculations. In experiments you don't do much calculations, but computational things requires you to do calculations. Calculation cannot be done in anywhere. It should have some base. That base is basically quantum mechanical or molecular mechanics, right? And then this allows you to do high throughput scanning. If you want to discover a new material and you are searching something in the jungle, how do you search? You search with certain kind of a methodology, and that methodology is called what is called high throughput scanning. We'll discuss these aspects in a detailed manner, don't worry about it. And this high throughput scanning allows you to reach the goal or target much faster than trial and error. So using quantum mechanical, molecular mechanics tools, and you can actually use a machine learning based model with the data available with you a 2-day high throughput scanning. Once you have done the high throughput scanning, then you can use all kinds of algorithms for machine learning tools. This is what is the material development design, starting from Stalin error, which has a very low speed, and then if you mix these quantum mechanical tools, if you use only quantum mechanical, it will be also slow, because that requires a lot of computation to be done, and many cases these computations actually are very slow, even if you use a very fast computer. So you will probably require much faster supercomputer, and high throughput scanning also requires high speed computational tools. And finally, machine learning, which is combining this, can give you the fastest answer. So let us stop here. In the next lecture we will talk much more about these aspects.